In this video, I'm going to solve the problem 24 from chapter 19. Suppose 10 gram of oxygen gas is heated at constant atmospheric pressure from 25 degrees Celsius to 125 degrees Celsius. First question. How many moles of oxygen are present? So for this, we have to use the table which is given here for getting the molar mass of the oxygen. So the molar mass of the oxygen, here they mention as 32 multiply with 10 to the power of minus 3 kilogram per mole. In the second question, we are going to find how much energy is transferred to the oxygen as heat. The molecules rotate but do not oscillate. In the third part, we are going to find what fraction of the heat is used to rise the internal energy of the oxygen. Okay, so now I'm going to answer one by one. So first of all, I'm going to write the given. So what is given in the question? In the question, they give the mass of the oxygen gas. So what is the mass of the oxygen gas? The mass of the oxygen, here they mention as 10 grams. So if you convert it in terms of kilogram, which is 10 multiply 10 power minus 3 kilogram. And they mentioned this is an oxygen, so it's a diatomic gas, right? So oxygen O2 is a diatomic gas. Diatomic gas. And they mentioned the process which takes place under constant pressure. So what is the condition? It is constant pressure. And the initial temperature T1, here they mention as 25 degrees Celsius, and the T2 mentioned as 125 degrees Celsius. If you need, you can convert it in terms of Kelvin, because the change in temperature either in Celsius or Kelvin will give the same answer. So I don't want to convert in terms of Kelvin. We can use the temperature in terms of Celsius. Clear? Okay, let's start with the first question. In the first question, we are going to find how many moles of oxygen are present. So let's start with the first question. So part A. So for finding the moles, we have to use the rule. What is the rule? Number of moles, N equal to the mass of the oxygen. So mass of the substance. So what substance we are using here? We are using the substance here as oxygen. So the mass of the oxygen over the molar mass of the oxygen, or molecular weight of the oxygen, right? Molar mass of oxygen. So now I'm going to substitute the value. The mass of the oxygen here they mentioned as 10 power minus 3 in terms of kilogram, over the molar mass of the oxygen, here they mention as 32 multiply 10 power minus 3 kilogram per mole. So 32 multiply 10 power minus 3. So this 10 to the power of minus 3 get cancelled, and finally we got 10 over 32. So if you just divide, we will get the answer 0.313 mole. Clear? So here the unit, the mass is in kilogram, and here the unit is kilogram per mole, right? So kilogram per mole. So this kilogram get cancelled, this mole will go to the top. By that you will get the answer in terms of mole. So the answer for the first part, the number of moles of oxygen, that means the number of moles of oxygen here they mention as 0.313. We got the answer. This is the answer for the first part. Clear? This is O2. Okay. Now we have to come for the second part. In the second part, we are going to find how much energy, heat energy, how much energy is transferred to the oxygen as heat. So for that, we have to use the rule, because the condition here they mention as constant pressure. So we have to use the formula NCP delta T. And this is a diatomic gas. So the Cp for diatomic takes the value of 7 over 2 times of R, right? And we have the number of moles, so I am going to take the answer from the first part, because we need the number of moles of the oxygen gas. And T1 and T2 is already given here. So T1 takes the value of 25 degrees Celsius and T2 takes the value of 125 degrees Celsius. So we have all the data. Now I am going to substitute the value of Cp here as well as the temperature. So N 7 over 2 times of R multiply with T2 minus T1. Now I'm going to substitute the value. in the first part, we got the number of moles here as 0.313, 0.313 multiply with the 7 multiply with 8.314, which is a gas constant, multiply with 125 minus 25. So this is a final temperature minus initial temperature over 2. Clear? So let's see what is the answer for the heat. So here I got the answer as 910.7 joule. So this is the answer for the second part, right? Okay. Now we have to go for the third part. What is given in the third part? What fraction of the heat is used to rise the internal energy of the gas? So that means we have to use the fraction. That means we have to take the energy as well as the heat energy as well as the internal energy. So for finding the answer for the third part, so I'm going to use the internal energy over Q. This is the fraction, right? And as we already studied the rule for change in internal energy, which takes the rule NCV delta T, and likewise the heat energy rule is NCP delta T, right? Now we can see this, we can cancel N as well as delta T and delta T. And we know CV for diatomic. So what is the value for CV for the diatomic? CV for the diatomic is 5 over 2 times of R, and CP for the diatomic, which is 7 over 2 times of R. So I'm going to substitute this value here. By that, the above expression will become change in internal energy over Q, heat energy, equal to 5 over 2 times of R over 7 over 2 times of R. So gas constant, we can cancel both top and bottom, as well as we can cancel this 2 with 2. And finally, we got the internal energy over Q. Finally, we got the internal energy over Q as 5 over 7. So what is the value of 5 over 7? The value for 5 over 7, we got the answer as 0.714. What's the value? 0.714. So this much fraction is the answer. If you want to find the answer for this change in internal energy, it's very easy. Just take the Q and just multiply here, because Q we already find the previous part. But for this question, the answer is 0.714. We are just finding the fraction. Clear? That's it. Thank you.